Today we're looking at how to find volume of a rotated area using calculus. It's carbon, aluminum, copper, lutetium, sulfur. So there are basically three methods you can use. I'm looking at a generic graph of 1 minus x squared, and then it's going to be enclosed by the line of x equals 0 and x equals 1. We're going to rotate that around the y-axis. So let's look at the first method. The first method is called the disk or washer method because we're pretty much taking each disk by rotating. We're summing each disk up. And usually it's used for partitioning for anything perpendicular to the axis of revolution. Because each rectangle here, it's perpendicular to the y-axis. And the radius for each disk is going to be square root of 1 minus y squared. Square root of 1 minus y. Because we solve for x in terms of y. And we know the x coordinate value will be your radius. And the thickness will be delta y, because the thickness of each disk is the difference between the y value. And then now we will set up a volume for a generic disk. It will be pi r squared. So it will be pi, the quantity of the square root of 1 minus y squared times delta y. And then if you take the limit of the Riemann sum of the volume of disk, you will get the definite integral of this. And then if you want to verify the answer, you can try another method and see the volume if it's the same. So let's look at the second method. The second method is called the shell method because we're trying to sum up the volume of individual shells. And for this, we would have to have a rectangular partition that's drawn by rectangles that's parallel to the axis of revolution. Because we're rotating the area around the y-axis, the rectangle is actually parallel to the y-axis. And if you rotate that, we can see this is a generic shell. Each shell would have an average radius of the x-coordinate, the height of the y value, and the thickness of the dx, the delta x value. So now we can set up the equation. The average radius should be x, and the altitude should be 1 minus x squared because y equals 1 minus x squared. That's from the graph. And the thickness will be delta x. So when you set up the volume of one generic shell, it should be 2 pi, because 2 pi times x will be the circumference of the shell, and 1 minus x squared is the altitude of the shell times delta x. And if you take the limit of the Riemann sum of all the volumes of the shell, you will get a definite integral of 2 pi from 0 to 1 of x times the quantity of 1 minus x squared times dx. And then the volume from the shell method and the disk method should be the same if you set up the integral correctly. Now let's look at the slice method. Because when we rotate that solid, we will see that if you get the cross-section that's perpendicular to the y-axis, you will get disks. And then if you know the area of each cross-section and the thickness of each cross-section, and multiply that and sum all those cross-sections up, you will get the total volume. So first we would have to find the area of a cross-section. The area of a cross-section will be pi r squared, which is this circle. And that would be pi times this quantity of the square root of 1 minus y squared. And the thickness of each disk or slice will be delta y, because we're taking the slice with respect to the y-axis. So the volume of one slice will be pi r squared times delta y, which is pi square root of 1 minus y squared times delta y. If you take the limit of the Riemann sum of all the volumes of the slices, you will get the volume is equal to pi times the definite integral from 0 to 1 of 1 minus y dy. And if you look at this integral is this exact same integral as the disk integral, which means we set up both correctly.